Hi everyone, and welcome to another episode of Chemistry with Wikipedia. Today I will be doing a tutorial on the ideal gas law. So we'll talk about the law itself and then how to solve problems using the ideal gas law. So the ideal gas law is PV equals nRT. P is pressure, V is volume, N is moles, and T is temperature. So those are our four variables. Volume must always be measured in liters. Moles must always be measured in moles, and temperature must always be measured in Kelvin. If your temperature isn't a Kelvin temperature, then you can add 273 to the Celsius temperature to get the Kelvin temperature. The last letter here is R. R is the gas law constant, and it's based on the unit of pressure. So pressure can be measured in ATM, torr, or millimeters of mercury. So if your pressure is measured in ATM, then the value that you'll use for R is 0.08206. If your pressure is measured in torr or millimeters of mercury, the R value that you use is 62.4. So this chart tells you which value you use for the value of R based on your pressure unit. These units behind R are just the units of R. These are designed so that they will cancel with all the other units and give you whatever unit it is that you're looking for. We don't need to be super duper concerned with the units of R. As long as you do your algebra correctly, your R units will cancel to give you whatever unit it is that you're looking for. So we've got PV equals nRT and the gas law constant. And then we also have another version of the ideal gas law. So if we take the ideal gas law and we replace N with moles over molar mass and rearrange our equation, we can use this to solve for molar mass. So this equation is molar mass is equal to dRT over P. PV equals nRT is our Pivnert equation. MM equals dRT over P is our M dirty P equation. So here, mm stands for molar mass, D is for density, T is for temperature, still in Kelvin, and then pressure is whatever it is, and then R is based on pressure. Molar mass is measured in grams per mole, and density is measured in grams per liter. If you are not given the density, then you can easily solve for the density because density is just mass over volume. So it's an easy enough calculation to do. All right, so how do we know which one to use? Pivnert is our standard for the ideal gas law, so most of the time you'll be using Pivnert. If the problem mentions molar mass or density, or if you're asked to find the identity of something, then you need to use M dirty P because we identify elements based on their molar mass. So anything with density, molar mass, or identity of element, we use M dirty P. Anything else, we use Pivnert. Even if it's asking for mass, we're still going to use our Pivnert equation because we don't have a direct mass calculation here, whereas it's really easy to go from moles to mass using Pivnert. Okay, so let's do some problem solving. So this says the volume of 3 moles of ammonia gas with a pressure of 0.95 atm and 324 Kelvin. All right, so there's not really anything involving molar mass or density, so I'm just going to use my Pivnert equation, and my p-value is 0.95 atm. V is what I'm solving for, so this is going to be my variable x. N 3 moles, and T is 324 Kelvin. So things to check for is, first I want to make sure that my temperature is in Kelvin. It is in Kelvin. And then I need to look at my R value. So to find R, I look at my pressure unit. My pressure is in ATM, so if I look at ATM, the value of R that goes with ATM is 0.8206. So now I have all my variables, and now this is just algebra. I have 4 out of the 5 numbers in the equation, so I can just solve for the 5th one. So here you can solve either way. You can plug everything in and then figure out what variable you're solving for and do it that way. I'm going to rearrange my equation to solve for the variable that I want first, and then I'll plug everything in. However you do it doesn't make any difference. As long as your logic is reasonable, you will get the right answer. All right, so I need to get volume on a side by itself, so it means I'm going to divide both sides by P. So I get V is equal to nRT over P. All right, and then I can just plug that in. N is moles, which is 3. R is 0.08206. T is 324. And P is 0.95. All right, so we put all of this into the calculator and we get 83.960. And then we need to put this into significant figures. So 3.0 is 2 sig figs, 0.95 is 2 sig figs, 324 is 3 sig figs, so the least number of sig figs here is 2. So my answer will be in 2 sig figs, meaning that my volume will be 84 liters. Let's do another. At what temperature will 12.4 moles of air occupy 315 liters at 808 millimeters of mercury? So again, here there's no mention of molar mass or density, so we're just going to use our standard PV equals nRT. All right, and then P is going to be 808 mmHg. V is 315. N is 12.4. T is what I am solving for. And R is based on pressure. Pressure is in mmHg, so mmHg means 62.4. So I'm solving for T, so I need to get T on a side by itself. So I'll divide both sides by nR, and I get T is equal to PV over nR. All right, so now I plug in. P is 808, V is 315, N is 12.4, and R is 62.4. All right, so we plug this into the calculator, and then here we have this situation where we have two things multiplied in the denominator. So when that happens, it's best to put everything in the numerator in one set of parentheses and everything in the denominator in one set of parentheses. All right, if you put them in separate parentheses, then your calculator may not realize that you need to put the 62.4 in the denominator, so you'll end up getting the wrong answer. So it's easiest if you just put all the stuff on top in one set of parentheses, all the stuff on the bottom in one set of parentheses as well. And so when we do that, we get 328.939. And then our sig figs are all 3, so my answer here is going to be 329 Kelvin. This doesn't say to put it into a Celsius temperature, so we can just leave it in Kelvin. If you want to put it back into Celsius, then you have to subtract 273, which is easy enough to do. All right, this says at what torr pressure will 0.875 moles of oxygen gas in a 19-liter container have a temperature of 35 degrees Celsius. All right, so again, we don't have any mention of molar mass or density, so I'm just going to use PivNerd. All right, so my pressure here is what I'm trying to find. So that's going to be my X value, and it tells me that I want to find the pressure in torr, which is important because that's going to tell us which gas law constant to use. And then volume is going to be 19 liters. N is 0.875 moles. T is 35 degrees Celsius. And R is based on pressure, which we said we're going to measure in torr. So that's going to be 62.4. All right, so this time our temperature is not given to us in Kelvin, so we're going to need to add 273 to the Celsius temperature to get the Kelvin temperature. So that's going to give me 308 Kelvin. And now I have what I need to solve. So since I'm solving for P, I'm going to divide both sides by V, and I get P is equal to nRT over V. And so we plug in 0.875 times 62.4 times 308 divided by volume, which is 19. All right, so we do all of that math and we get 885.09. Check our sig figs. So this is 3 sig figs, this is 3 sig figs. This looks like it's 2 significant figures, but the thing of it is that we didn't put the Celsius temperature into our equation, we put the Kelvin temperature into our equation. So when we added 273, the rules of addition are that we look only at what's behind the decimal place. Since 35 doesn't have any digits behind the decimal, our answer won't have any digits behind the decimal, so our answer here is 308, which when we multiply has 3 significant figures, so my total answer here is 3 significant figures. Most of the time, your temperature will end up being 3 significant figures. Even if the value that's given to you is in Celsius, when we add the 273, it's almost always going to end up being 3 significant figures. All right, so 3 sig figs means that my answer here for pressure is going to be 885, and that unit was torr. Awesome, awesome. All right. How many moles are needed to occupy 14.8 liters at negative 28 degrees Celsius with a pressure of 2.48 atm? All right. No mention of molar mass or density, so I'm just going to use my Pivnert equation. P 2.48 atm, V 14.8 liters. N is what I'm solving for. T is negative 28 Celsius. And R is based on P, which is an atm. So that means I'm going to use 0.08206. All right, and then my temperature is in Celsius, so I'm going to need to add 273 to get it into Kelvin, and that's going to give me 245 Kelvin. So again, here, even though there's 2 sig figs here, when I put it into Kelvin, it's 3 significant figures. So let's rearrange our equation. We're solving for N, so we're going to need to divide both sides by RT. So I get N is equal to PV over RT. P is 2.48, V is 14.8, R is 0.8206, and T is 245. So again, when we put this into the calculator, because there's 2 things in the denominator, we want to make sure that when we put these in parentheses, we put it in one set of parentheses and not 2 separate parentheses. All right, so when we do all of that math, we get 1.8256. And so we've got 3 sig figs, 3 sig figs, and 3 sig figs. So my answer here will be 1.83 moles. All right, determine the Celsius temperature of 82.3 grams of CO2 contained in a 22.5 liter vessel at a pressure of 975 mmHg. So here there's no mention of molar mass or density, but we do have grams that we're given, and we've never seen grams before. So if we kind of use our process of elimination here, V is volume, P is pressure, T is what we're finding. So this 82.3 has to be somehow related to moles. So if we think back, we can use our molar conversions to take grams and convert them into moles of CO2 using the molar mass. All right, so if we'll set up our equation here, so we have PV equals nRT. P is 975 mmHg. V is 22.5 liters. And for N, I have 82.3 grams of CO2 times the molar mass of CO2 is 44.01 grams, and that is equal to 1 mole. If you are having trouble figuring out how to find molar mass, there's a video on that. You should go back and watch it. If this molar conversion looks completely foreign to you, then you should go back and watch the video on molar calculations where I go through how to solve this. All right, so when we do this, and we are going to put our answer here in 3 significant figures, we get 1.87 moles. All right, and then T is what we're solving for. Okay, so then R, lastly, is based on pressure, which is in mmHg, so it's going to be 62.4. All right, so we are solving here for temperature, so we'll divide both sides by nR, and we get that T is equal to PV over nR. So we plug in 975 for P, 22.5 for V, N is 1.87, not 82.3, and then R was 62.4. Right, so again, since we have 2 things in the denominator, we want to make sure that we put all of that into one set of parentheses. And when we do all of this, we get that our temperature is equal to 188 Kelvin. But it's asking for Celsius temperature, so to convert from Kelvin to Celsius, we subtract 273, and we get negative 85. So our temperature value here will be negative 85 degrees Celsius. To convert into Kelvin, we add 273. To convert out of Kelvin, we subtract 273. Let's look at this. This says, what mass of xenon is present in a 10-liter vessel with a pressure of 1350 torr at negative 17 Celsius? So here again, we have a mention of mass, nothing about molar mass, nothing about density, nothing about the identity of the substance. So we can just use our plain old Pivnert. So it's asking for mass. So if we kind of look at this by process of elimination again, pressure is in 1350 torr, volume is 10 liters, N is not given, which means that this is what we're solving for. So even though we're solving for N, if it's asking for mass, we're going to have to take our moles and then convert them into mass using molar mass. And then our temperature is going to be negative 17 degrees Celsius. And then for R, we look at our pressure is in torr. So this is 62.4 for our R value. All right, we do need to convert our temperature into Kelvin. So negative 17 plus 273 equals 256 Kelvin. All right, so again, I'm going to solve for moles. So I'll divide both sides by RT, and I get N is equal to PV over RT. All right, and then we plug in 1350 torr, N liters divided by 62.4 and 256. So here we have two things in the denominator, so we want to put that into one set of parentheses. The value that we get for N here is going to be 0.845 moles. All right, but our problem is asking us for the mass. So to convert mass to moles, we use the molar mass. So 1 mole on the bottom to get moles to cancel. Xenon is an element, and if we look at the periodic table, it has a molar mass of 131.29. All right, so when we do that, we get 110.953, and we're looking at 1350 only has 3 significant figures because with no decimal place, that 0 is insignificant. 10.0 has 3 significant figures because it does have a decimal place, which means that the zeros are significant. And then our temperature is in 3 sig figs as well. So our answer here is going to be 111 grams of xenon. This says, what is the molar mass of a gas that has a density of 3.81 grams per liter at 557 torr and 429 Kelvin? All right, so this time we are given information about molar mass and density. So that means that we're going to need to use our m-dirty-p equation here. So the molar mass is what I am solving for. And then D is density. That's 3.81 grams over liters. T is 429 Kelvin. P is 557 torr. And then R is based on our P value. It's in torr, so R will also be in torr, so that's 62.4. Our density is in grams per liter as a unit, but that we don't do anything with that. Those are just the units of density. It doesn't mean that we have to do any additional work. Our temperature is already in Kelvin, so I don't need to do anything there either. So I can actually just use the equation as written because I'm solving for molar mass. So molar mass will equal density 3.81 times R, 62.4, times T, 429, divided by P, which is 557. And then when we do this, we get 183.109. And then we've got 3 significant figures all around. So my molar mass will be 183. And then the units for molar mass are grams per mole. All right, so this says, what is the density of NH3 gas at negative 25 degrees Celsius and 683 mmHg? So here we are solving for density. So again, we're going to need to use the m-dirty-p equation. So molar mass is not given, but we can't have 2 variables. We're already solving for density, so we can't also solve for molar mass. But what I do know is that it's NH3 gas. So I do know how to find molar mass, so I can find the molar mass of NH3 gas. And I find that to be 17.04. N is 14.01. Each hydrogen is 1.01. And so we add them all together and we get 17.04. All right, density is what I am solving for. It's my X. T, negative 25 degrees Celsius. P is 683 mmHg. And Our R is based on mmHg, so it's going to be 62.4. Right, and then I do need to convert my Celsius temperature into Kelvin, so that's going to be 248 Kelvin. Right, so since here I am solving for D, I need it to isolate my density. So since P is in the denominator, I'm going to multiply both sides by P, and I get mmP is equal to dRT. And then I need to get density on a side by itself, so I'll divide both sides by RT. So I get D is equal to mmP over RT. Right, and then we plug in. MM is 17.04, P is 683, R is 62.4, and T is 248. So again, since I have two things in the denominator, I'm going to make sure I put everything into one set of parentheses. And when I do that, I get that the density is 0.75206. All right, so our significant figures here, we have 4, 3, 3. So 3 is going to be our sig fig situation. So D is equal to 0.752, and the units of density are grams per liter. All right. This says which gaseous element has a density of 2.048 grams per liter at 157.2 Celsius and 3.582 atm. So here it's asking for the element. So to find the identity of something, we need the molar mass. So we're going to need to use m dirty P and solve for molar mass. So that's going to be our unknown. All right, so density is 2.048 G over L. T is equal to 157.2. P is equal to 3.582 atm. So our R is based on atm. So this is going to be 0.08206. All right, and then I need to add 273. So when I do that, I get 430.2 Kelvin. Even though 273 doesn't have any digits behind the decimal, this is a constant, so anytime that we add or subtract from a constant, we don't really pay attention to it. It has an infinite number of significant figures, so we just look at our given value, which has one digit behind the decimal, so my answer will also have one digit behind the decimal. We are already set up to solve for molar mass, so we just plug in. MM is equal to D, which is 2.048. R is 0.08206. T is 430.2. And P is 3.582. So when we do all of this, we get 20.81395. And then we've got 4 sig figs, 4 sig figs, 4 sig figs. So my answer will have 4 sig figs. So the molar mass here is going to be 20.18 grams per mole. And then as for which element is this? So if we look at our periodic table and we look for 20.18, we find that the only element that has a molar mass of 20.18 is neon. So that means that my element here will be neon. All right, and let's do one more. This says what diatomic gas in a 50-liter tank at 85 Celsius will weigh 59 grams when the pressure is 823 torr. So this is asking us for which gas, so that again is the identity of something, so we'll need to find the molar mass. So we'll use m dirty P and solve for molar mass. Density is not given here, but we can't have two variables, so we can use our density equation, which is mass divided by volume. So the mass that's given here is 59 grams. The volume that's given is 50 liters. So when we do that math, we get that our density is 1.18 grams per liter. All right, and then T is 85 degrees Celsius. P is 823 torr. And then R is based on P, which is torr, so that's going to be 62.4. And then we need to convert Celsius into Kelvin, and we get 358 Kelvin for that. And then we solve, so mm is equal to D, which we said was 1.18, R 62.4, T is 358, and P is 823. All right, so when we do this math, we get 32.029, and then everything here is 3 significant figures. So my answer here will be 32.0 grams per mole. So here it asks for which diatomic gas. So we're looking for an elemental gas here, but since it's diatomic, that means that this molar mass is actually for 2 of that. So diatomic means that there's 2 of those elements, so it means we need to divide this by 2, and we actually get 16 for our molar mass, which, if we remember, is the molar mass of oxygen. So our answer here is oxygen, but since there's 2 of them, it's going to be O2. All right, there we go. All right, so that is the ideal gas law. This has been another episode of Chemistry with Capadia Tutorial Edition. I hope you learned something, and until next time, keep on chemin'.